Hello. See how many people are showing up. So far, there are only 5 of you. Maybe I should have tested you on this material. Maybe I should give you a last homework or something. Anyway, so let's wait another minute or so. If there's not enough interest in these lectures, then I may not bother. Oh, people are showing up finally. Okay. So how was your Thanksgiving break?
Well, it was not actually a break for me.
To relax a little bit? Relaxing, okay. Chelsea said she, at least one of you found it relaxing. I had to grade your exams during Thanksgiving break, so it wasn't that relaxing for me. Although you guys did pretty well, except for the last question, like I said in my email to you. All right, let's get started, I guess. So the last couple of lectures before the second exam, we talked about. Let me maybe remind you of that. So, talked about subgradient, so-called subgradient descent algorithms, and then one thing we found was that the subgradient actually may not necessarily be a descent algorithm, but still it can work if you choose your step size appropriately. Okay, and so again, if the function is convex, and then you apply this subgradient method with diminishing step size. So the alpha k's have to go to 0 at some rate. Then you can show that basically you're exploiting convexity to show this. You can establish that you can make the iterate converge to the optimal solution x star. But of course, in order to make that happen, you need to make the alpha k's go to 0. And if you make the alpha k's go to 0 at an appropriate rate, then such that this ratio goes to 0, then we can actually prove convergence, right? And the rate of convergence that we found was, depending on how you choose the step size, if you choose it as 1 over k, then you get a rate of convergence. It's really slow, 1 over log n. You can improve this log n to square root of n if you choose an alpha k that goes as 1 over square root of k. And this is pretty much the best you can do. Okay. Even with even if you assume stronger conditions in the function and so on, you pretty much can't get around the 1 over square root of n type convergence. Okay. So today we are going to discuss a way to, in some special cases. So in general, you can't get around the 1 over square root of n, right? But in some special cases, you might be able to get back to the rate of convergence you get when you have a gradient. Okay, so that's what we're going to talk about today. So that's called the proximal gradient method. And the reason why these kinds of methods have become popular recently is because in many applications, you do have what you do is you add a function. So you're trying to optimize some function, say g of x, and this g of x might be convex and continuously differentiable. But then you add something called a regularizer to this function. And the regularizer may be convex. Typically it's convex, but may not be differentiable everywhere. So subgradients exist because it's convex. Okay, and we'll talk about this a little more detail towards the end of the lecture. But say if one example that we saw of a convex function in your homework exercise and also in class before is the L1 norm, right? So if h of x is equal to summation of the components, absolute value. So this is the L1 norm. Okay, then this is something that's convex, but it's not differentiable, right? But you can easily find the subgradients of this function. Okay, and we saw examples of that. Okay, so let's see how we can deal with this. So we have a combination of functions now, but if you look at this sum total of g and h, you get f, because h is not differentiable everywhere, f is also not going to be differentiable everywhere. F is convex because it's the sum of convex functions, but it's not necessarily differentiable everywhere. So you can, of course, apply the subgradient method, and like we saw last class, but then we saw that at a rate of convergence that's not good. So if you want to approach f of x star, then you have to make n become much larger than you would the square of what you would have to use if you just had g of x without the h of x. Okay, but you want to add this h of x because h of x actually gives you some interesting properties in certain machine learning applications and compressed sensing and so on. Adding something like this is very useful. Okay, so let's see how we proceed with this. So we use a trick called the proximal gradient method. And in this iteration, what you do is, let's look at, suppose we didn't have h of x, then gradient descent will look like this, right? Xk plus 1 is xk minus some alpha k times the gradient at xk of g. So now suppose what happens if h of x is not 0? What we'll do is use a proximal gradient estimate. So proximal is that, what do we mean by proximal? So what we do is we let xk plus 1 minimize h of x. Okay, so at each iteration we try and minimize h of x, but we want to keep the minimum value, right? Xk plus 1 is the argument of this function, minimum value close to the gradient of g. That's why it's called the proximal gradient method. So basically in each iteration you're kind of trying to be as close to the iterate that you would have had with just g, but you're also trying to minimize h simultaneously. So you take a combination of these two things, and this turns out, this way of forming xk plus 1 turns out to give an iterate that under appropriate conditions you can make this iterate actually converge to the minimum of the sum at a rate that's much better than 1 over square root of n. Okay, right? So it's called a proximal method because you're trying to keep close to the gradient descent step that you would obtain if you only had the function g, which was differentiable. So this is the penalty. It's a quadratic penalty, similar to the penalty method that methods we've studied previously, right, in the course. So there's a penalty for deviating from the gradient iterate alpha xk minus alpha k gradient of g of x. Okay. Now there's a scaling, and that scaling actually turns out to be important. We'll see why that's important when we actually use it in the iterate. Okay. All right. So what's the catch? Anyone can see? What's it?
You have to find the minimum.
Yeah, so you have to find the minimum of this function, right? But at least it's a quadratic function, right? I mean, well, it's a convex function, strictly convex function, right? So this guy, it's quadratic and x. So this part at least is not well behaved, and the h of x is a convex function. So this is a convex optimization problem, but this is actually a very special kind of convex function, right? For which maybe if the h has a certain simple form like this L1 norm, and we'll look at this example in detail at the end of the class, then it turns out that this minimization can be actually done in closed form. It's easy. So you don't have to, there's no, it's basically, you just have an expression for it. Okay? There's no iteration or anything that you need to do do this minimization. Okay, so that's the inherent assumption. So if the h of x is such that this minimization is easy, and it turns out to be the case for many interesting h, then of course we can compute the iterate easily. Okay, so the inherent assumption here is that h is such that this minimization is easy. In fact, you would like it to be in closed form. You don't want to have to do any iterative procedure to find this. If that's the case, then you're going back to using if you have to use a gradient method or this gradient type method to solve this optimization problem, you're going to go back to the original 1 over square root of n type of behavior. Okay. All right. So let's assume now that this optimization is easy. Okay, and so we can find an xk plus 1. That's the minimum of this function. Is that clear? Okay. All right. So what do we do then? First, what we do is we write the solution in a form that looks familiar to you. So xk plus 1 is some quantity that's the minimum of this function. I can always write it as xk minus alpha k dk, where dk is basically xk minus the solution xk plus 1 that you just found divided by alpha k. Okay, so if you set dk like this, then I could write the solution xk plus 1 as xk minus alpha dk. So the reason for writing it this way is that now the iterate can be thought of as some kind of generalized gradient descent step. So dk is like a generalized gradient at xk. Okay, everyone okay with that? I haven't really done anything. I've just written xk plus 1 in a it's in a different form just for convenience. Then I can write the algorithm and its convergence and so on in terms of dk. Okay, so xk plus 1 is written as this. Right? All good? Okay. So now let's assume that G has Lipschitz gradients and use a constant step size alpha. You can do the same proof without the Lipschitz assumption or without knowing the Lipschitz constant. and then you'd have to use backtracking. So, but essentially the proof goes through and you get the same rate of convergence as long as you have convexity. Okay, even if you don't know the Lipschitz constant. Okay, so so of course, if we know the Lipschitz constant, we can use the descent lemma, and we saw several applications of the descent lemma. Whenever you have Lipschitz gradients, that's the first step that you use in proving convergence of things, right? And you saw that actually in the last question of your exam as well. So from the descent lemma, we can write g of xk plus 1 in terms of g of xk, and basically this alpha dk comes in this first term, and then you have the quadratic approximation, right? So it's upper bounded by this quadratic approximation by the descent lemma, right? Okay. So now this xk plus 1, which I wrote as xk minus alpha dk, minimizes this quantity. So remember, this is a convex function where this part is differentiable, this part's not. Right? But this part's differentiable. So since it's a convex function that has it has subgradients, and what's a condition for a minimum? Remember this from lecture maybe 20?
0 needs to be an element.
Yeah, there it is. 0 has to belong to the set of subdifferentials, right, at x star. Okay, so we'll exploit that condition. First of all, also, if I have a function that's differentiable and add something that has subgradients, what's the subgradient of the sum? And we saw this as a sum of the subgradients. But of course, the first component has a gradient. So there's only one thing to consider there, which is the gradient. And here you'll have a set of possible values. Okay. So let's first compute the gradient of the first component. So this is going to be 1 over alpha times x minus xk minus alpha. Okay, so that's the gradient of this guy. And the subgradient, let's call that v, and v belongs to some subgradient of h of x. And what we know is that since it's the minimum has 0 has to be a subgradient, so 0 has to equal the subgradient, which is the gradient here at x. So xk plus 1 is the one that's doing this. So let's write that as xk plus 1. Since xk plus 1 is the minimizer, or is a minimizer. Actually, it is the minimizer. Why? Unique? Why is that? Anyone?
Strictly convex?
Strictly convex, right? It's strictly convex. And so this is this plus v for some v belonging to the subdifferential at xk plus 1. Right? Since xk plus 1 is the minimizer, it must satisfy this condition. Okay, so let's simplify this. So xk plus 1, this is basically xk minus alpha, alpha times dk. That's how we wrote it. So when you simplify this, the xk cancels and you're left with 0 equals gradient of g of xk minus dk plus v for some v belonging to this, right? Or you can write this as v equals dk minus gradient for some v again, for some v in the different. All right, so that's what it means for xk plus 1 to minimize this quantity. We'll actually look at some specific v when we'll actually exactly specify what v is when we look at specific functions h. Okay, a little bit later. All right, so we have this. So we have v equals this. Now we make use of the definition of the subdifferential. By the definition of subdifferential, we know that h of x for any x in Rn is going to be lower bounded by the first order approximation, right? With respect to the subdifferential. That's a definition of subdifferential. So since v belongs to, v is one of these things that belongs to the subdifferential, or v is subgradient, so this has to hold. All right, so now we'll substitute what v is in this equation. So v is dk minus gradient of g of xk. All right, and then we'll take it to the other side. So h of xk will be gradient of g of xk minus dk transpose x minus xk plus 1 plus hx for all x belonging to Rn. I'll call this equation 1. Okay. Okay. And we're slowly getting there. So we now have something here. This is the h part of it at the new iterate. But we already, from the descent lemma, we already had the g part at xk plus 1 in terms of g of xk, right? So let's use that. And so, oh yeah, and then we'll explore the fact that g is convex. So from convexity, I can write g of xk in terms of g of x for any x in Rn. So convexity of g, I'll write it in terms of g of x, but then I have to add to it the gradient of g of xk transpose times xk minus x. Okay. All right. So basically, I'm exploiting the fact here that g of x will be bigger than g of xk plus gradient of g of xk transpose x minus xk. So I brought that to the other side because I have g of xk here. I want an upper bound. So I get that. Okay. And then I still have these other pieces. So I'll have minus alpha gradient of xk transpose dk, and then the half L alpha squared dk squared. This holds for all x belonging to Rn again. So this I'll call equation 2. All right. Okay, so now I have these two equations, equation 1, equation 2. I'll add these two equations. So on the left-hand side, I'll get the sum of these two, but that's just nothing but my function f, right? And then I have, on the right-hand side, I have h of x plus g of x. That's also my function f evaluated at x. And then I have a dk transpose this term here. Let's look at this term here, dk transpose x minus xk plus 1 with a negative sign. So I'll write that as plus dk transpose xk plus 1 minus x. And then I have well, I'll keep this term here, half L alpha squared dk squared. And then the last term to consider is the term that has all the gradient of g of xk. So this is plus gradient of g of xk transpose. I have an x minus x, xk minus x from this term here, and then an x minus xk plus 1 term. And then I have another term here, which is minus alpha dk. Okay. Anyone see anything interesting about this last term that I just wrote down? I saved the best for last. Yeah?
Is it 0?
0, yeah. So it's 0 because basically this cancels with this, and then xk plus 1 is xk minus alpha dk. So this cancels with these. So this whole thing becomes 0. Right? So you just get the first 3 terms. And here, what I'm going to do is write xk plus 1 in terms of xk again, minus alpha dk non alpha k. I've decided to use a constant step size. Okay, so if I did that, then I'll get f of x plus dk transpose xk minus x, and then I'll have an alpha dk squared, or minus alpha dk squared rather. And then a half right? So we have this, and this again, all this holds for all x belonging to Rn. And that's important because I'm going to take 2 special cases of this x in just a minute. Right, so far so good? So I use the sub-differential property of H and the minimization to be able to see what happens to H when I go from step K to step K plus 1. And I used the descent lemma on G because it's a Lipschitz function to figure out what happens to it when you go from step xk to xk plus 1. Then I combine the 2 to figure out what happens to F. Okay, and this is what I found. Right? All right. Let's see how this is useful. Okay. So this is what we have. We just, from the previous page, we got this. Now, let's make our alpha smaller than something. And again, it'll depend on the Lipschitz constant. So let's make alpha less than 1 over L. As L will be less than 1 over alpha. Then what happens is that this term here, there's an alpha here. I want to match it with this guy here. So if I make alpha less than 1 over L, not 1 over 2L, but 1 over L, sorry, not 2 over L, as you would in regular gradient descent. You have to make it a little bit smaller. Then this term and this term will combine, right? And I'll end up with, I could make it a little bit larger if I like. I could make it closer to 2 over L, but I can't quite get to 2 over L. That's all. Okay. But if I do that, all I need is some kind of constant that still sits in front of dk squared with a negative value in front of it. So I need to make sure that this still stays negative, okay, with this term added. So if I make it 1 over L, then it just becomes half alpha. Okay, but I could actually choose a slightly larger step size too. Okay, so suppose I did this, then what happens? Then you see that if I set x equal to xk, if I set x equal to xk, then what happens here? This term goes away. This is just true for all x. So I'll set x equal to xk, and then I just get that f of xk plus 1 is less than f of xk minus alpha over 2 dk squared, which is of course less than f of x, because the second term is negative. What does this mean? This means that if alpha is chosen to be less than 1 over L, then this algorithm is what kind of algorithm?
Descent.
It's a descent. Okay, so you're using a generalized direction, decay, but as long as your alpha is less than 1 over L, it's actually a descent direction. Actually, it doesn't have to be, it can be closer to 2 over L, but it's okay, but 1 over L works. Okay, so that's good. That's different from, you already see some difference now between this and subgradient method, because subgradient method is not a descent algorithm, right? No matter how small you make your alpha, because there could be some subgradient directions that are bad, right? Whereas this, by combining these two, we do have a descent algorithm. So the fact that you have a descent algorithm also means that I can use backtracking. Okay, even if I didn't want to use constant step size, if I didn't know the Lipschitz constant, I can always use backtracking to ensure that I go down. Okay, is that clear? All right. So now, what the other thing we do is, so this stuff inside this box is useful in 2 ways. One is that it's useful in showing that it's a descent algorithm. The other thing that's useful for is saying how close I can get my xk plus 1 to x star. So if I set x equal to x star on the right hand side, and I get this. Okay. All right. So I'm going to rewrite that as just alpha over 2 dk squared minus this. But I noticed that this is in a form of that maybe I can write it as a quadratic by completion of squares. So I have a square term here and have a middle term here. So to complete the square of this term, there's already a 2 here. I need xk minus x star divided by alpha squared. Okay. So what I'll do, and if I do complete that square, what I end up when I complete that square is dk minus this term. So everything without the dk, 2 over alpha x minus x star. Right? Sorry, not 2 over alpha, just xk minus x star divided by alpha. The 2 is part of the middle term. So this would be dk minus, or maybe I'll write it the other way. Xk minus x star divided by 2, divided by not 2, divided by alpha, minus dk. So that's the complete square, and then I have to subtract out the term that I added to complete that square, which is xk minus x star divided by alpha. Right? And you can go back home if you're at home and verify that if I complete the square, if I expand this out, I'll indeed get this. Okay. All right. So now I'll take the alpha squared out from both of these guys, and I'll get the first term will be xk minus x star minus alpha dk squared, and then that should be, sorry, that should be I don't know why I put a plus there. It should be a minus. I'm not sure. That's wrong. That should be a minus, sorry. Okay. So this is basically xk plus 1 minus x star squared minus xk minus x star squared. Right. Yeah. So any questions so far? Does this look familiar to anyone? Look like something we did a long time ago. Maybe I don't remember which lecture did we do this in. It's lecture 7, maybe. See if I can find it. Oh, actually, we were discussing this before, right before the exam, so I have it open here. So yeah, so this is starting to look like this expression here. F of xk minus f star is this, right? But you don't have this term here. Okay, so let's go back to our lecture. So, so if you take the difference between f of xk plus 1 and f of x star, you have this term on the right-hand side. Okay, that's what you have. Okay, so now actually we just use exactly the same steps that we did in lecture 7 for proving the 1 over n type convergence for a convex function. Why? Exactly the same conditions hold as in lecture 7. So we have something that's descending. So we have since it's a descent direction, f of xk plus 1 is less than f of xk. That's a condition we already have for our new algorithm. And then we have on the right-hand side, we have this telescopic sum. Okay, we don't have to worry about this term. Okay, so we have this. So those two things together are enough to prove what we need. Okay, we follow exactly the same steps. Okay, so we'll sum on both sides, and we have the telescopic sum again, like we've had, and actually in several proofs we use this trick. And then you're left with only the first term and the last term. Okay, and of course this last term doesn't matter because it's negative, so I can upper bound it just using the first term. And then to handle the left-hand side, we make use of the fact that it's a descent algorithm. So f of xn plus 1 is less than all the other guys. Okay. So then we have that if we replace it by the smallest value here, if you replace each term in this thing by the smallest value, which is xn plus 1, this will be upper bounded by this summation. In other words, if I take each of these terms and lower bounded by xn plus 1, they'll all be the same term, which is this, and there's n plus 1 elements, so you say n plus 1 times this is less than this. But this, we know is less than that. Okay, so from that, we get that n plus 1 times f of x, this guy, is less than this. So I'll take the n plus 1 on the right-hand side, and I get 1 over 2 alpha n plus 1 x 0 minus x star squared. So this is order 1 over n. Right? Does it seem like magic?
It does.
It does, right? It's a little bit like magic, but it only seems like magic because we assume that we could solve this optimization problem easily, right? We assume that this guy can be solved easily. Okay, so we'll now maybe we'll take a short break, and after the break, we'll see how we can actually solve this easily for the L1 optimization problem. Yeah, this is a very clever trick, I guess. So when and it's actually quite a relatively recent idea in optimization. Because a lot of the stuff we learned in this class is more than 50 years old. And one of the main drivers for this algorithm was modern techniques like compressed sensing and lasso and things like that used these so-called L1 regularizers. Okay, and we'll maybe say a little bit more about that at the end of the lecture. All right, so let's take a short break, unless you have any questions about the steps here. Okay. All right, take a short break and we'll be back at 11:42. Okay. All right. So let's look at how we can solve this optimization problem. But it's sometimes called the proximal function. This function that you're trying to minimize. So how you minimize this function in closed form. Okay. So we'll only look at this specific example. You can generalize this to other kinds of h of x that are similar in a similar family, and that's like instead of L1 norms, you can use other norms. But I'm not going to talk about that. The L1 is the simplest one to deal with. So we'll do that. Okay, so in order to set that up, so this is a minimization over x. Okay, so this is just some other vector. Let's call that z, right? So I'm just doing it at some time step k. So this is some vector z. So xk minus alpha times the gradients of. Okay, let's just call that z. So we really want to minimize this quantity here. Okay. But what is this? I can rewrite this as, so this I can write as the summation from I equal to 1 to n. So since I use subscripts for denoting iterations, okay, to avoid confusion, I'm going to just use this parentheses notation for the components of the vector, because, you know, I think somewhere in lecture 1 or something like that, I said there are alternative ways to represent the components of a vector or matrix. You can use subscripts or you can use parentheses. So we'll now use the parentheses notation just to avoid confusion with subscripts. So that's how the norm squared, the L2 norm squared, is defined, the sum of the differences of the components squared, and this h is the sum of, actually I already defined that up there. So this is the sum. Yeah, the sum of the absolute values of the xi's. Okay. So the minimization problem can be written like this. You want to minimize the sum. I just combine the two sums together. So it's this quadratic term plus this absolute value. But if you look at this, I'm trying to minimize this over the components of x, all the components of x. But each term in the summation only depends on one of the components of x, xi, right? And these terms in the summation are all non-negative. Okay, so minimizing the sum of these non-negative terms where each component is controlled by a separate variable is equivalent to minimizing each term in the sum separately. So for each I, couldn't say this if some of the terms could have been negative, but since they're all non-negative, you want to make them all as small as possible, but each one can be controlled by a different variable. So they don't, you can't change one of the other components by changing, say, you can't use x1 to change the component corresponding to x2, right? So you can only use it to minimize the first term, x1. And similarly, x2 can only be used to minimize the second term. So for each I, you want to solve the minimization problem, minimize. But this thing here, this function that I want to minimize for each I, I'll call C of X. Okay, this is a convex function, but it's not differentiable at x equal to 0, right? At xi equal to 0. So you have to use, you have to be careful depending on where the minimum occurs, right? So let's consider different cases. So let's consider first the case that a positive value of x is optimal, okay? So xi bigger than 0 is optimum. Then, having xi be positive means that C of xi is this plus xi, right? The absolute value is replaced just by xi itself. And so since that's optimum and my function is convex and differentiable, the gradient has to be 0, or the derivative has to be 0 at that xi. But the derivative being 0 at xi, that condition just says that xi minus zi divided by alpha plus 1 is equal to 0. From which you get that xi, let's call that xi star, is not to be confused with the x star, which is the minimum for the function f. This is just the x star for this minimization for the proximal function. Okay, and of course this is going to be the solution only if xi star is positive. That means this is a solution when zi is bigger than alpha. Similarly, xi less than 0 is optimal, means that now C of xi in this case would be this quadratic minus xi. The absolute value of xi will become minus xi. And in this case, it's easy to see that the solution will just be zi plus alpha. Okay, instead of minus alpha, it becomes plus alpha. And this is the correct solution if zi is less than minus alpha. So if zi is bigger than alpha, all right, if zi is bigger than alpha, this is the solution for xi star. If zi is less than minus alpha, this is the solution. So what do you think happens when zi is in between minus alpha and plus alpha? So these two cases cover the cases when xi is positive and xi is negative. There's only one case left.
xi 0.
Xi equal to 0. And xi equal to 0 is optimum whenever we hope that whenever zi is in the range from minus alpha to plus alpha. And we'll see that that's the case. Okay. And here now we have to use subdifferentials, right? Or subgradients. Right? So the condition for optimality of xi equal to 0 says that the subdifferential must include the point 0. So the subdifferential at 0, as we know, we can write the subdifferential as the sum, or subgradients as the sum of the gradients of the two terms. Subgradients of the two terms. The first term is differentiable, so I should maybe be a little careful here and write down what C of xi is. So C of xi in this case is equal to zi squared no, sorry. Yeah, no, I want the derivative at 0. So let's be. So yeah, so the first part is differentiable. So this guy here in xi minus zi divided by alpha, I'll just, xi is 0, then I'll just get minus zi divided by alpha. So if I look at the subdifferential, I need the derivative. So it's minus zi divided by alpha from this first term. And then for the second term, the absolute value of xi at 0, the sub differential. Remember what is the sub differential at 0 for this kind of function? Absolute value of x.
-1 to 1.
-1 to 1. So this is this for v belonging to -1 to 1. Right? So 0 must belong to this for xi equal to 0 to be optimum. This means that minus zi plus alpha plus v must equal 0 for some but this can happen if and only if zi belongs to minus alpha. Okay, then we can always find a v such that zi divided by alpha equal to v belonging to the interval -1 to 1, such that minus zi or alpha plus v equal to 0. Make sense? Okay, so that's nice. All three cases are easy, and we end up with this final equation. So what does this look like? So xi star, which is basically xk plus 1, right? That's a definition of xi star. Or the definition of xk plus 1, that's a minimizer, so it's xi star. If zi is less than, bigger than alpha, sorry, and it's 0 if minus alpha is less than equal to zi less than alpha, and it's zi plus alpha, zi is less than minus alpha, or minus, not infinity, minus alpha. Okay, there we go. So what does it look like? If you plot this, it looks like this. So for all alpha, all z bigger than alpha, basically you start at 0 and then you increase linearly at a 45-degree angle. Same thing below minus alpha, you start at 0 and then decrease a 45-degree angle. But in between, you've zeroed out z completely. Okay. So this kind of operation is called a shrinking operation or a shrinkage operation. So xk plus 1 is obtained by shrinking zi to 0 in some alpha neighborhood of 0. Okay, and this kind of shrinkage operation actually appears a lot in many signal processing applications, modern signal processing applications, okay? Where you basically, if a value falls below a certain threshold, in this case, the absolute value falls below a certain threshold, then you just zero it out. Okay, and that this kind of thresholding, hard thresholding, is actually turns out to be have some very nice properties, okay, in many applications. So this is called a shrinkage operator. So you shrink zi towards 0 to form your solution xk plus 1. Right? But again, it's a very straightforward solution. So in order to find xk plus 1, you start with, you take the gradient step. You take the gradient step and just that you would get with g, and just shrink it towards 0. And you're done. Because the shrinkage here only depended on alpha, but that's only because I didn't put any parameter here. So if I put some h of x, I put a lambda here or something like that, some constant, multiplying the L1 norm, which is typical in applications, then the shrinkage operator will also depend on that. Okay. Any questions? Okay, but in any case, it'll always look like this. This is what you do. You take your gradient iterate that you would have had with just G and modify it just in this manner, and then that's your iterate for the proximal gradient step. Very simple. Okay. So it turns out the problems of this form, but F is I should have called this G. G of X plus lambda times the 1 norm, L1 norm of X. This appears in many modern applications. Okay, one of the places it appears is something called lasso, where this G of X is what you would use to minimize when you're doing some kind of linear regression. So linear regression is you try to take a set of data points and you try to find a linear function that best approximates those data points. Okay, so for that linear for linear regression, this actually turns out to be a quadratic function, because you want the approximation to minimize an L2 norm essentially. So this G of X turns out to be a quadratic convex function, but then you may want to limit the number of features that you use in this approximation. So X kind of is the vector of parameters that determines your approximation, and so you want that X vector to actually have as few non-zero components as possible. And it turns out that adding this L1, so-called L1 regularizer to the optimization makes sure that you get rid of features that are not that important in the linear regression approximation. And it actually makes the regression perform better, and it's less noisy, and so on and so forth. So that's where this kind of optimization arises in machine learning. It also naturally arises in compressed sensing problems. Some of you might have encountered that. Maybe it's in the papers that you're looking at for your project, you might come across it there, where you essentially what you're trying to do there is find an approximation to a vector, again, that has as few non-zero entries as possible to explain something. And there, what you do is you replace, so actually what you're interested in was what's called an L0 optimization problem there. Okay. L0 norm is basically the number of non-zero elements in a vector. Okay, you want to keep that as small as possible in your optimization, and it turns out that replacing the L0 optimization problem is essentially a highly non-convex hard optimization problem. But it turns out that relaxing the L0 norm to L1, you can show that you do get a so-called sparse solution with few non-zero entries, and that again, that's where a problem like this might arise in that context. Okay, so many problems where many modern applications where optimization problems like this arise, which is why these methods, these proximal methods, and the shrinkage operations are very useful. Okay. Any questions? questions? Got something useful out of this?
I have a question.
Yeah.
Why would you use, if both the L1 norm and the 0 norm favor smaller, fewer features, why would you use the L0 norm?
So the only, okay, that's a good question. So the L1 norm can be shown to favor, or produce exactly what the L0 optimization produces under certain conditions. Okay, it might favor smaller values, but it may not produce exactly what the L0 norm problem. You were originally interested in solving the L0 problem, okay, but it turns out to be computationally hard. But you can show that under certain conditions on the function that you're optimizing, that the L1 problem and the L0 problem have exactly the same solution. Okay. Okay. If you can show that, then you by relaxing from L0 to L1, you have not lost any optimality. But in general, you might lose something by that relaxation. So the theory involves showing that relaxing L0 to L1 is okay, but in practice, you would just use the L1 optimization and solve it using a method like this. Does that answer your question?
Yes, thank you.
Anyone in class doing a project or reading a paper about some of these kinds of methods, lasso or compressed sensing? No? Okay. Well, we'll see. Maybe some of you haven't thought about your project enough yet. All right. So on Thursday, we're going to talk about another application. Actually, we focus only on the application on Thursday, which is a machine learning method called support vector machines. Okay, and we'll see how the constraint optimization problems that we studied earlier are going to be useful there, and in particular why duality is very important. Okay, that's a very good example to illustrate the power of duality. So we'll do that on Thursday. I'm not sure exactly what we're going to do next Tuesday yet. I thought about a few topics, but they're either not that interesting, or they're a lot more complicated, and they will go a little bit beyond the scope of this course. So, but if you have anything you want me to talk about, just let me know, and I'll try and prepare some notes for that. And otherwise, we can just either not have a class next Tuesday, and so you could sit down, and for those of you who are working on your projects, or if you have other final exams, you can use that time to prepare for those exams, or we can just have a general discussion to close out the class. So just let me know. Okay. All right. So see you on Thursday.